Good evening, everyone, and welcome again to SocialFlight Live. We have a great show for you this evening. Mike Busch is back with us, CEO of Savvy Aviation. If you don't know Mike Busch, then chances are you've been probably hiding under a rock somewhere or not really that into aviation, because the bottom line is that he is the best known A&P and IAA in general aviation. He writes a monthly Savvy maintenance column for AOPA Pilot, hosts free monthly maintenance webinars for EAA, and he, of course, runs Savvy Aviation with all of their services, which we'll talk about a little bit towards the end of the show, where he can help you analyze all of your problems, provide services on the road, pre-buy, all sorts of other things to help you. And of course, the number of accolades that Mike Busch comes with is just too many to list, but the bottom line is he was honored as the National Aviation Maintenance Technician of the Year by the FAA Administrator back in 2008, been a pilot and aircraft owner for more than 55 years with over 8,000 hours logged, with ratings from commercial, single, multi-engine, seaplane, glider, CFII, and of course A&P and IA. Welcome, Mike. How are you?
Did I hear my name mentioned?
Yeah.
Good
Well, I
evening.
really appreciate you coming back. This has become a staple here on SocialFlight Live to have you on the show, and we are going to talk Engine Diagnostics tonight,
Yep.
and there's no one I respect more about that than you.
We got a good turnout tonight. Look at that.
Yeah, well, hey, you're a great
Excellent.
draw. So, you know, when we talk about engine diagnostics, I figured a cool flow for the evening would be to think about it the way a flight actually goes and focus on the different things. So let's start with starting. Hard starting. What are some of the things that come to mind for you, for people that have challenges and issues around that?
Well, there are two different kinds of issues with hard starting. One has to do with when you try to start the engine and the prop doesn't turn.
There you go.
And the other is when the prop turns but the engine won't start. So let's take them one at a time. If you try to start the engine and the prop doesn't turn, or it just twitches or something like that, then you either have a problem with the starter motor, or you have a problem with the battery, or you have a problem with the starter drive adapter, the thing that couples the starter to the engine. Now, Lycomings have a pretty simple starter drive adapter. It's basically a gear engagement system that's either engaged or it isn't engaged. When Lycomings have a problem in this area, typically what happens is you turn the key, you hear the starter turning at some ungodly high RPM and nothing's happening. And it's because the Bendix drive is not extended and engaged in the ring gear. And that's because it got dirty. And typically you just spray it with some spray solvent and clean it up a little bit and everything works fine. Some of the more modern Lycoming starters use an enclosed thing that doesn't get as dirty as the older styled ones. Continental has a very peculiar starter drive adapter. I'm not sure who invented it, but it basically is a system where the starter turns a big giant coil spring that is wrapped around a knurled drum called a shaft gear, which is geared to the crankshaft, and it works kind of like a Chinese finger trap. The idea is when the starter starts to crank, the spring tightens up on the shaft gear and engages it kind of like a weird clutch, turns the crankshaft, and then once the engine fires and the engine's turning faster than the starter, the spring kind of releases its grip on the shaft gear and the whole assembly freewheels, so that the starter doesn't have to run and the engine doesn't drive the starter going backwards. Mm-hmm. And it's sort of a peculiar arrangement. It works okay, but doesn't work so well if the inside of the spring or the outside of the shaft gear have worn.
Right.
And when they wear, those things start to slip. And The shaft gears are kind of expensive. The starter adapter takes about 4 hours to change out. It's sort of a pain. If you get stuck with a Continental engine with a starter adapter that slips, and again, the way you tell that is you hear the starter motor turning, but the prop is just twitching. It's not getting past a compression stroke. Then the way we usually get our clients home from a situation like this is not to have the starter adapter replaced, but to get the FBO to bring over an APU card and hook the airplane to 14 or 28 volts. Because what we found is that a starter adapter that's slipping on battery voltage 12 or 24 will usually have another half dozen starts left in it at higher voltage, where the starter is tightening the spring a little more aggressively because of the higher voltage.
That's
so
great.
Usually that's a really good way to get home or get to some place where you want to down the airplane long enough to have your starter adapter looked at.
Let me ask you, do oil additives play into this at all? I mean, on one hand, you're trying to get as slippery as possible with a bunch with additives. On the other hand, the starter adapter relationship in there with that spring is one that needs a little bit of friction.
Yeah, there's it is a delicate balance, and there is a history of synthetic oils, and actually the only full synthetic that is Mobile Av 1 hasn't been on the market for some years, but semi-thin synthetic like Aeroshell 15W50 aggravating starter adapter slippage in Continentals. There are a number of reasons that we don't particularly like Aeroshell 15W50 in these engines. It doesn't work real well with leaded fuel either. It tends to cause more lead deposits, but it also does have a history of aggravating slippage of the Continental starter adapters. So we prefer oil that's 100% petroleum based,
like a Phillips 66.
Yeah, Phillips XC or a Phillips Victory oil if you want a multi-grade oil, or plain Jane Aeroshell W100, which is what I've used in my airplanes for about 50 some odd years. Works real well.
Okay, but no issue.
I'm not aware of any additives that create problems. I use CamGuard, for example, in my engines.
I do too.
Which has a number of friction modifier additives in the package. It doesn't seem to cause any problem with starter adapters, but synthetic oil has had a history of having a problem.
Any issues before we move on to other diagnostic stuff that or any news? I mean, I know there's a new starter adapter, I think, out there. Hopefully that's even better.
I'm not aware of one that's even better. There are several varieties of Continental starter adapters, but they all work on the same principle, and they all seem to the same problems. Now, so that's the part of starting where the prop doesn't turn over. The other half is starting when the prop does turn over, but the engine doesn't start. Basically you need three things to get an engine running. You need fuel, air, and spark. Air is never a problem when you're sitting on the ramp at sea level, so you can kind of cross that one off the list right away. So normally the starting problem is either fuel related or air related. Fuel for starting has to do with how you're priming the engine. And if you're not giving it enough prime, or what's more commonly a problem, if you're giving it too much prime, the engine won't start because the mixture is too rich to burn. So if you have a persistent problem of hard starting, the chances are pretty good that it's an ignition problem. And again, that kind of breaks down a little bit as to what kind of ignition system you have. Right. Most of our engines are driven by mechanical magnetos, and there are two starting systems for mechanical magnetos. One is the Bendix shower of spark system, which requires kind of a glorified doorbell buzzer to generate the spark. It's a pretty good system. That's what I actually have my 310. But if the buzzer goes bad, you're going to have problems starting.
Yep.
And I had one failure of the starting vibrators, what they officially call the buzzer, in my 310. And basically the symptom was you'd crank, and nothing would happen, and then you take your finger off the start button, and immediately the engine would start. That was sort of made it pretty clear that it was the starting vibrator. The other system that is used is impulse couplings. If you turn your prop by hand and you hear a clicking sound, you've got impulse couplings, and that's a deal that involves a spring and a pawl and a centrifugal fly weight that starts the engine when you crank the engine at starter speed, 50 RPM or whatever it cranks. The mag's not turning fast enough to generate a spark that will jump the spark plug electrodes. So what the impulse coupling does is it winds up a spring as you crank the engine, and then when the spring gets wound up a certain amount, a pawl releases and snaps the mag over under spring tension at a much faster RPM than what the engine is actually turning. And it also has the effect of retarding the spark, which you need to get the engine started. It's a mechanical device, and like all mechanical device, and it's one that wears over time. So there are a fair number of problems with impulse couplings, and that can be a cause of hard starting. Some engines with impulse couplings use impulse couplings on both mags.
Right.
And so if you have one that's worn and one that's not worn, you still have a pretty good chance of getting started. Other engines use impulse couplings on only one mag, and they only start on a single mag. And then both mags come in once the engine gets started. And in those engines, I'm thinking of a Piper Cherokee, for example, that I think only starts on a single impulse coupling. If that impulse coupling starts malfunctioning, it's a kind of a single point failure as far as starting is concerned.
Right. Yeah, I think grounds do that too, and I think it grounds out the other magneto that's not the non.
I don't know if they were trying to save money or weight, but it gets rid of some redundancy that would be very nice to have.
Yeah, although I guess part of the what you're getting at there is that if you have a dual impulse coupling system and you're seeing a degradation in how your starting is going compared to how it used to go, you may want to check it out, because you may be halfway to failing if one of those two is doing that.
And then speaking of the ultimate loss of redundancy, there's the Bendix dual mag that we find on Lycoming engines that have a D at the end of their model number have the dual mag, which has a single drive and a single impulse coupling, driving basically two magnetos packaged into one case. Wasn't really a great idea. Probably shouldn't have gotten certified in the first place, because it really defeats a lot of the redundancy. And what's worse, the mags were made by Continental, and they were only used on Lycoming engines. What's wrong with this picture? So basically, Continental decided, hey, only our competitors use this mag, so they decided they're going to stop supporting it. And now people with dual mags have a very serious problem keeping them.
I think we might need to have a show at some point where we take all the very bad ideas along the way, and it'd be great to have the folks on, if they were still around, that ever came up with those, just to get some answers.
Yeah, exactly. You might have to have two shows to cover all of those.
That's right. So that at least gets us to there. I mean, now the other thing is that sometimes, you could talk for a while about hot starting. Do you have any thoughts about a situation where someone would be having a hot start issue where normal, proper procedures aren't solving it? There is something going on about the aircraft that's making it especially difficult. Is there anything you'd look at there?
Well, I mean, hot start problems normally are due to a vapor lock someplace in the system, and um, I know a lot about hot starting Continental engines because I've been flying behind Continental engines for 55 years. I'm not quite as expert at hot starting Lycomings, but there is a really surefire way to hot start a Continental engine if all of your normal, and I don't usually do this, by the way, normally just cranking it without priming it or without doing very much priming, we'll get it started. But if you have a persistent hot start problem, and some airframes are more prone to this than others because it really has more to do with the engine installation than it has to do with the engine.
Mm-hmm.
But if you have a persistent hot start problem with the Continental, you just can't get the thing started. There's a surefire method that invariably works, and that method consists of basically putting the mixture control at idle cutoff, putting the throttle all the way in, and running the boost pump on high for about a half a minute.
Yep.
And what that does is it takes cool fuel from the tank, circulates it all the way through the system, all the way through the fuel pump, the fuel control unit, and because the mixture's at idle cutoff, all that fuel then gets returned back through the fuel pump and back to the tank. And so everything in the fuel system all the way up through the fuel control unit now gets cooled by running the pump for half a minute or so.
Got it.
And the only thing that's left that you haven't purged yet is that little piece of the fuel system that goes from the fuel control unit to the flow divider and into the fuel nozzles. So then just the slightest blip of pump with the mixture control advanced will put cold fuel through everything else. And it needs to be a very brief blip or you'll flood the engine.
Right.
And that basically takes care of the vapor lock problem, and the engine ought to start normally.
And I've found that technique to work very well as well. And in all else, if you have a situation where it starts to run and then it starts to die, just like you said, a little blip of the fuel pump will usually just push right through any of the vapor that's trapped and do that. So, all right, we've got our engine started. We're climbing out and temps are up.
You want to talk about if we got our engine started and it's running rough?
Sure, let's do that.
And before we launch off into the sky,
that's right. Before we launch off in the sky, we've got like a stumbling, let's say a stumbling Lycoming engine in the beginning.
Yeah. So you finally started the engine. This is a cold start, first flight of the day, and it's running, but it's running real rough. And then as it warms up a little bit, it smooths out. And by the time you've taxied out to the run-up area, everything seems normal. That's the symptoms that we colloquially refer to as morning sickness for obvious reasons. And it's normally caused by a sticky exhaust valve in one or more cylinders. And it's a warning sign. It, like I said, normally clears itself up by the time you get to the run-up area, but it's an early sign of a problem that's developing that if you don't react to it, can actually cause some significant engine damage, and in some cases can cause in-flight emergencies and forced landings and all off-airport landings and stuff, bent push rods and bad things. So if you have an engine monitor, you start the engine, it's running a little rough, you turn on the master switch to power up the avionics, including your engine monitor. And you look at the EGT display and you discover that there's some cylinder that's not making EGT.
Right.
And then eventually it'll start making EGT when the valve frees up. The reason this is always worse when the engine is cold is because the clearance between the exhaust valve stem and the exhaust valve guide is tightest when the cylinder head is cold, and it loosens up as it warms up. So because valve sticking is caused by the accumulation of deposits on exhaust valve stems, that makes it hard for the valve to move smoothly in the guide. The situation is always worse with cold cylinder head temperatures, and it gets a little bit better with warmer cylinder head temperatures. So that's why the symptoms are the way they are.
Right.
And they're much more common in Lycomings than in Continentals, although they sometimes occur in Continental engines, but a lot more in Lycomings. In fact, I wrote a whole article on titled "Why Valves Stick" that's, I think, in the most recent issue of AOPA Pilot magazine, that talks about the chemistry of what causes those buildups and why they're more prevalent in Lycomings, and what pilots can do to minimize the buildup. But if you do have experience morning sickness, it's a really good idea to have it looked at before it gets bad enough that it can damage anything, or maybe even damage you.
Yeah, and that's something, I mean, from my days with Grummins and Lycomings, I'll say it's, really important to stay ahead of that, because that's one of these key maintenance areas where there's things you can do before you have a problem. There's lots of processes, and I know that there's a valve wobble test. I have one of those fixtures that is available, where your mechanic can check what the play is in the valve, see if you have too much play, too little play, what's going on. And there's things that they can do generally fairly easily to remedy it before you get yourself into trouble. So that certainly makes a lot of sense.
Right. It is important to note that the problem that causes morning sickness, the sticking valve syndrome, can generally be remedied without removing the cylinder.
Right.
It does require taking the valve train apart, and it does require taking the valve train at least partially apart in order to do the wobble test. And so actually I recommend doing something that's less invasive than that to begin with, and that is regularly bore scoping the cylinders, which you should be doing anyway, but bore scoping, but including in your bore scope exam, looking at the exhaust valve fully open, where you can visualize the lower part of the valve stem and get a pretty good idea of how much crud is built up on there. And that also gives you some pretty good feedback on your power plant management technique, because there's a lot you can do as a pilot to minimize the accretion of those deposits, which are actually lead oxybromide deposits. And by leaning the engine very aggressively during taxi and idle and other ground operations, and by keeping your cylinder head temperatures in the sweet spot, somewhere in the upper half of the 300 Fahrenheit range, you will reduce the amount of deposit buildup, and hopefully forestall this problem from happening, or at least making it happen a lot less often.
Yeah, and so you can solve it, as you just mentioned, by inspecting it, seeing it, changing your habits before you get there. You can solve it by, if you don't catch it at that stage, you can go through the process of still leaving the cylinder on the engine. There are things where you can check it, you can remit, other things can be done. And hopefully you avoid the worst consequence, which of course lots of people unfortunately have experienced, and I have friends that unfortunately ran into this, don't know how, where it sticks and it can actually stick out and get hit by the piston. So bad things can happen.
Yeah, you can, something's got to give. If the valve sticks closed, then the push rod's probably going to bend, and that will put the cylinder permanently out of commission. And four-cylinder Lycomings don't run very well on 3 cylinders. If the valve sticks open, that's even worse, because there's a potential for what you're talking about, which is a valve strike, where the piston comes up and strikes the valve, which is supposed to be closed, but it isn't. And that can snap the head off of the valve stem. And if it snaps it off just right, and it isn't your lucky day, I've seen a number of cases where it causes a disintegration of the piston and a really catastrophic engine failure. In fact, I know of at least 2 fatal accidents that were caused by that. It's not a high probability event that the the head of the valve that snaps off the stem has to lodge itself just in at the right angle in order to cause the piston to disintegrate. But it has happened a couple of times, so it's nothing to fool around with.
What about rough running that's unrelated to this Lycoming morning sickness?
Okay, well, it's kind of interesting. I know of a lot of cases where people will complain of a rough running engine, and mechanics will wind up changing magnetos, changing carburetors, and all sorts of things. And they don't quite understand that a rough running is a very specific symptom, and it means something very specific. It means that not all the cylinders are making the same horsepower. So something that affects all cylinders equally, like a carburetor or like a magneto, can't possibly cause rough running. It can cause all sorts of other stuff, but it can't cause the engine to run rough. So if an engine runs rough, we want to look for something that is affecting just one cylinder or just a couple of cylinders. So for example, a problem with a fuel injector obviously can cause rough running. An induction leak can cause rough running because it'll cause, one or two cylinders to run way leaner than the other cylinders. An ignition problem is less likely to cause rough running simply because even if one spark plug isn't firing, the engine normally will run just fine on the other spark plug. So that's a less likely scenario for rough running, just because we have the redundancy there. But when we're looking for the cause of a rough running engine, what we should be looking for specifically is something that affects only one cylinder or just a couple of adjacent cylinders, something like that.
Okay.
And components that can affect all cylinders equally are not good candidates for being the cause of rough running.
Got it. Okay, so that makes sense. So you're looking at the things for individual cylinders and what could be causing an individual cylinder to be having a problem. And when you're looking for horses instead of zebras, you don't think like one bad spark plug. It would have to be two in that case. So it's less likely.
Exactly. And when we hear about rough running in crews and stuff, one of the most common cases is one or two cylinders that are lean outliers compared to the other, rotten mixture distribution.
Right.
And when we talk about the flight test profiles a little bit later, we'll talk about how we test for that and how we determine which cylinders are the leanest and whether they're much leaner than the others and stuff. But ideally, we would like all the cylinders in an engine to run at exactly the same mixture. That they never do quite that, but we want them to be pretty close.
Got it. So so now we are at that stage of takeoff, and so now we're climbing out. A couple different things we can talk about, totally separate. First, what do you look at when you've got issues having to do with not getting the power output that you would expect to get?
Well, I mean, that's not a very common complaint that we get, mostly because, to be honest with you, pilots aren't very good dynamometers. It's amazing how much performance an engine can lose without a pilot noticing it. We have seen some situations where people say, this airplane's just not climbing right, and then it turns out that there's some incredibly horrible problem going on.
Wow.
But pilots aren't very good at detecting subtle losses of performance. The sort of thing we will, the kind of complaint we'll get most often at that phase of flight, takeoff, initial climb, is that the cylinder head temperatures are too high.
Right.
And it's actually good that we're getting those sorts of complaints, because it means that my 20 years of trying to pound into people's heads the notion that we have to be careful about cylinder head temperatures is starting to bear fruit.
Yes.
But if the cylinder head temperatures are too high, there are basically two things that can cause cylinder head temperatures to be too high. one is that the cylinders aren't getting enough fuel,
Right.
and the other is that cylinders aren't getting enough cooling air. And it's usually very, very easy to determine which is the case, because if the problem is that the cylinders aren't getting enough fuel, then when we get to the cruise phase, they're not going to be running hot anymore. And another test that we like to do is to run the engine at a rich peak mixture for a while. Notice what all the cylinder head temperatures are. Then lean it to a lean peak mixture and note what all the cylinder head temperatures are. If a cylinder changes rank, that is, if it was the hottest, for example, rich peak, and it becomes the coolest lean peak, what does that mean? Well, that means that cylinder was running a whole bunch leaner than the other cylinders. So just doing a quick check of the cylinder head temperatures, rich peak and lean peak, will tell you almost immediately whether you have a lean outlier cylinder.
Right. And that brings us also to, I think, something that's really important, and that's proper fuel setup on, of course, Continental engines.
I was going to get to that. In Continental engines, the fuel injection system is highly adjustable. There are 5 different screws that you have to tweak to get the Continental fuel system adjusted correctly. And I actually like the fact that it's highly adjustable, because it means that we can set it up just the way we want it. But it's very important to have it set up correctly. And it's astonishing how often we see Continental powered aircraft that are taking off with inadequate fuel flow, simply because nobody adjusted the system correctly. Continental, well, it's partially that, and it's partially that Continental's service documentation leaves a little bit to be desired. And in this sense, if you look at Continental's guidance on how to adjust the fuel injection system, which used to be something called SID 97-3, and now it's incorporated into their manual M0. It will give a range of takeoff fuel flows that are acceptable. It shouldn't do that, and that's a real problem, because when confronted with a range, mechanics instinctively aim for the center of the range. Yeah. But what Continental says, if you read the fine print, is we want you to adjust it to the top of the range.
Right.
The reason we're giving you a range is that if it's at the bottom of the range, it's unacceptable, but we want it to be at the top of the range. We even prefer to see the fuel flows on Continental engines just at about a half a gallon an hour greater than the top of the range, just to provide a little extra cooling. But we consider the maximum that Continental specifies as kind of the minimum that you want to have, because we really don't want these cylinders to be cooking themselves on takeoff and initial climb. And oh, go ahead.
I was going to say, for my part, I think one of the challenges is, like you said, so few people actually have their mechanics that have the right equipment and are getting it set up on a regular basis. Right. There is a lot of just guesswork. I mean, you're talking very appropriately about be at the top of the range that Continental is setting here, things that you can do because of that. I'm shocked by the number of people that I have talked to and come across that have never had their had their engine set up properly. You need metered and unmetered fuel gauges outside the aircraft that are calibrated to do this process, as of course you know, but I want to make sure viewers know this as well.
And it's even worse. It's even worse for turbocharged engines, because you need differential pressure gauges, which very few shops have.
Right. And I have even seen where people read something or see something about needing the extra fuel flow, as you've mentioned. And I've come across at least one aircraft where they just cranked it up without using the proper things. And that actually gave them a performance problem, because when it was finally measured, the reason they were getting such poor performances, they were running so overly rich. They
Hmm.
were way beyond anything that it would be recommended that you start losing power again.
Yeah, yeah. Um, the uh, there's even a greater catch-22 here. Not only is the fuel flow at full power need to be at the top of the specified range, but the fuel flow at idle has to be at the bottom of the specified range. And again, all of this is in the fine print of Continental's stuff. But if you just look at the tables and you don't read the text, you won't get that. And it's very important to have the thing adjusted that way. There are also several other adjustments that you have to do, including the idle RPM stop, the idle mixture adjustment. On some turbocharged aircraft, there's an adjustment on a fuel limiter. It's a fairly complicated system to adjust, and it's worth taking the airplane somewhere that really knows how to do this.
Mm-hmm.
In fact, if you live anywhere in the Southeast, take it to Fairhope and let Continental set it up. But there are shops, various places in the country that know how to do this. But not every mechanic has the equipment to do it, and not every mechanic has the experience to do it. And probably the most important time to get this stuff adjusted is when you change the engine. It's about the
Right.
worst sin possible is to take an engine out of the crate from an engine shop, and they've sort of set it up roughly on their test stand, and then drop it in the airplane and assume that it's going to be okay. You really have to, it's super important to go through the full adjustment protocol when an engine is first put in the airplane.
Right. Right.
Continental actually calls for doing it every year. That's probably excessive. But certainly anytime there's any reason to question any time that there's an issue with, cylinder head temperature on takeoff, or the thing doesn't seem to be idling right, it's a really good reason to go have the adjustments gone through again.
Right. Now, I know that obviously it's a little bit different. It's dramatically different with carbureted engines, but there are options there where there have been certain carburetors that had a variety of different nozzles that could be put in them. What's the thought on that? What's involved in
Yeah,
what's the purpose of
and again, on a carbureted engine, it's really nice to have an engine monitor with fuel flow installed to be able to see what the fuel flow is. Typically, carbureted engines don't have any fuel flow gauges installed by the factory. But if we have, let's say a Cessna 182 and it's running high cylinder head temperatures, and we can see what the fuel flow is, and we realize that it's not getting enough fuel flow on takeoff, we'll recommend taking the carb, sending it to a good fuel metering shop, and having them rejet the carburetor to bring the fuel flow up to something higher. It's not quite as easy as with Continental fuel injection, where you turn a screw,
Right.
but it's doable, and it's very important for the longevity of the cylinders to
Right.
have that correct.
So obviously the other thing that if it's not fuel, it's air, and that I assume basically leaves baffling.
Oh, you're talking about cooling air. Okay.
Yeah.
I see. Yeah. And yeah, we see a lot of problems with baffle related problems in terms of not having adequate airflow over the cylinders. A couple of things about that. First of all, whenever you have the engine decaled, it's really important when you're cowling it back up to make sure that all the flexible baffle seals are pointed in the right direction when the cowl goes on. And it's really easy to screw that up if you're not paying attention to it. The the baffle seals have to be oriented in a way that when the upper part of the cowling pressurizes in flight, the flexible seals are pressed tightly against the cowl rather than being blown open and allowing air to leak. And so the orientation of the baffle seals is important, and it's particularly problematic if the baffle seals are allowed to get old and sort of flabby, because it's a lot easier for them to get misoriented if that's the case. Another thing is that frequently forgotten are the little inner cylinder baffles, which are the little bitty funny pieces of metal that sit below and between each adjacent pair of cylinders, and are there to prevent the air from being able to just whistle on down through the slot between the two cylinders without doing any cooling work in the process. And those are sort of out of sight and often out of mind. You have to get up on a ladder and stare down at them to see whether they're in place correctly. One trick that we often recommend to owners if they're having cooling problems is to put the airplane in a kind of a darkened hangar or something, stick a strong light down underneath the engine, maybe up through a cowl flap or something, and with the upper cowling removed, stand on a ladder and look down. Right. If you can see any light coming up, you got a problem. Okay, it means that there's something missing there. We don't want to be able to, if light can get from the bottom of the engine to the top of the engine, then air can get from the top of the engine to the bottom of the engine without going through the cooling fins, and that's where we lose. The cooling is remarkably fragile in these airplanes. It depends on a pressure differential between the upper part of the engine compartment and the lower part of the engine compartment. The baffles and baffle seals, partition the engine compartment into a high and low pressure area. And the differential pressure between those, which is what does the cooling, is only a very slight pressure difference. It's measured in inches of water rather than inches of mercury. And so any kind of even seemingly small leak where a baffle seal isn't pressing tightly against the cowling, where there's a grommet that's disintegrated somewhere where wires are going through the baffling, anything like that, that allow air to be able to sneak from the high pressure area to the low pressure area without going through the cooling fins, it's going to rob the engine of cooling air, and it doesn't take much of that to have a pretty significant effect.
Yeah.
I want to mention one other thing that we always want to look at whenever we get a complaint of high cylinder head temperature, and that is to check magneto timing. Magneto timing, if it is advanced, meaning more degrees before top dead center than the data plate says it should be, will cause a very significant increase in cylinder head temperature, and also is quite abusive on the engine. The tolerances for mag timing are very tight. I believe Continental specs mag timing to be something like +0 and -1 degree from the spec. And if you do the timing with one of those
flower pots,
old flower pot things that has a weighted pendulous pointer on it, it's really easy to be a couple of degrees off with that thing. If the pivot is a little sticky and the parallax is a little wrong and stuff. So we like to time the engines one of two ways, either with a good digital protractor, which are now like El Cheapo at Home Depot, and that measure within the nearest tenth of a degree, or on engines that actually have timing marks somewhere, like for example on the Permold Continentals in my 310, there's a little 7/8 inch timing plug you can remove, and you can actually see timing marks on the ring gear that drives the alternator. And so we like to adjust it one of those two ways rather than using an old flower pot, and make sure that any error is going to be on the minus side. In other words, If it has to be off, make it a little retarded rather than a little advanced, because
Right.
advanced is very hard on the hardware, and it also causes high cylinder head temperatures.
Got it. Got it. Now, the other thing, of course, when we talk temps is oil temp. So if someone's got a high oil temp, where are we going with that problem?
Well, we like to see oil temperatures running ideally somewhere between 180 and 200 degrees Fahrenheit. It's acceptable to be 10 degrees outside of that boundary, 170 to 210, but anything over 210 is too hot. It results in, now when I say too hot, it's not going to damage the engine. It's going to damage the oil. That's really why we worry about high oil temperatures, because if the oil runs too hot, it oxidizes at an accelerated rate. And if you do have excessive oil temperature, or if you are flying somewhere where it's really hard to keep oil temperature, like I've had a couple times when I was flying out of Las Vegas in the summer, and you sit on the ground with the engines running, waiting for clearance, and it's almost impossible to keep the oil temperatures in, within the boundaries that you want them to be kept. So if you can't avoid over temping the oil, then you should just change it more often, because the over temp damages the oil, and you want to get rid of it sooner. The oil is thermostatically controlled. There's a thermostat called a vernitherm that, if it's doing its job correctly, should be holding the oil temperature within fairly tight limits. Vernitherms can go bad. The seat in which the vernitherm is screwed into, so a vernitherm has a conical poppet valve at the end of it, and that screws into a seat, and the seat can conceivably be damaged. So one of the things we want to do when we're troubleshooting something like this is remove the vernitherm and look at the wear pattern on the poppet.
Yep.
And make sure that there's good contact all the way around, because there may be a problem there.
No foreign debris, anything like that.
The other possibility is that the vernitherm's working okay, but the oil cooler just doesn't have enough cooling capacity to handle the heat output of the engine. In which case the oil cooler may be clogged up. If it's been a long time since the oil cooler was last flushed out, it may be necessary to remove the oil cooler and send it off to an oil cooler place to have it cleaned. It's kind of important to understand how the whole oil system works. We think about oil as being a lubricant, but it does a lot more than that. And one of the most important things it does is it cools components of the engine that don't have an opportunity to get air cooled. And probably the most important components are the pistons. If you think about it, the pistons get really hot. They participate in the combustion chamber, and they don't have any cooling fins, and they don't have any air flowing over them. And the only thing that prevents them from going into meltdown is the fact that we're splashing a tremendous amount of oil on the bottom of them to try to carry off the heat. And in some engines, there are actually even nozzles called oil squirts that squirt oil on the bottom of the pistons, again, to cool them off. So of course, what that does is it cools the pistons off, it heats up the oil. And normally, as the oil circulates through the engine, it gains on the order of 40 degrees Fahrenheit in oil temperature. And then it goes through the oil cooler, which cools it back down by 40 degrees and dissipates that heat into airflow that's passing through the cooler. The cooler is just basically an oil radiator. So if there's not enough air going through the oil cooler, and that's another baffling issue, because one of the things that the baffles have to do is provide a pressure differential that forces air through the cooler, or if the cooler has some obstruction that isn't allowing the oil to flow freely through it, that can cause a problem. But the vernitherm is the first thing we want to look at, because that's the thermostat. That's the thing that's supposed to be regulating oil
And you
temperature.
look at that same thing, the vernitherm, which can also fail in a way that keeps your oil too cold as well. It doesn't block off your oil cooler when you need it as well.
Right. The vernitherm works sort of backwards as what you might think. It's a very simple device. It has this poppet valve, and it's got a little wax capsule in it.
Yep.
And the wax expands when it gets hot and contracts when it gets cold. And so the vernitherm and its seat provide an oil path that bypasses the oil cooler. So when the oil's cold and the vernitherm is retracted, oil freely bypasses the cooler, and so the oil doesn't get cooled.
Right.
Because we're trying to get it to heat up.
Right.
Well, when it heats up enough and it gets to say 180 degrees Fahrenheit, then the wax in the vernitherm expands and closes the poppet valve, blocks off the bypass, and forces all the oil to go through the cooler and to get cooled. And if the cooler is doing too much cooling, then the vernitherm will back off a little bit and let a little bit of the oil bypass, and it regulates the temperature that way. Well, if the poppet valve in the cooler is not making firm contact against the seat and isn't closing off that bypass, then you're not going to be getting the full cooling potential of the system, and the oil's going to be running hot.
Right.
So it's sort of a backward system. It's not modulating flow through the cooler directly. It's modulating flow that bypasses the cooler.
Yeah.
So it's working sort of backwards.
Well, Mike, I want to make sure that we have time to get to one of the things that I find fascinating, which is the work that you do with flight test profiles for people with engine monitors and all the things that you're able to diagnose from those in-flight tests. So I'd love to hear you talk about that for a little bit.
Okay, well, Savvy has a whole division that is dedicated to basically analyzing engine monitor data. It's probably about a third of all the business we do has to do with analysis, and as far as I know, we're the only people who do that kind of work. We've got developed a pretty elaborate IT platform that allows data to be uploaded and provides a bunch of graphical tools for looking at it and figuring out what it means. And we make the platform and all those tools available for free and to anybody who wants to use them. And there's 10,000 or so aircraft owners who regularly upload their data to our system. And a lot of them do analysis on a do-it-yourself basis. We also offer paid service for people who want to have our analysts look at their data and generate reports for them, and we generate all sorts of interesting reports. But one of the things that we like to our clients to do, whether they're paid subscribers or free subscribers, is to fly what we call a flight test profile, where they go through certain maneuvers with the engine controls, if you will, not maneuvers, not aerobatic maneuvers, but they manipulate the engine controls in a certain way that's calculated to capture data of maximum diagnostic value, so that after they come down from that flight and dump the data and upload it to the platform, either they, if they're doing their own analysis, or we, if we're doing the analysis for them, can learn the most that we can about what's going on with their engine. And there are a number of tests we do, but there are two primary ones I'll talk about. And one is the ignition system stress test, and the other is the mixture distribution test, or otherwise known as a GAMI lean test. The ignition system stress test, very simply, is just an in-flight mag check done at cruise power at the leanest possible mixture, preferably a lean and peak mixture, but the leaner the better. It turns out that the mag check that we're all taught as student pilots to do, in the run-up area just before we take off, is a test that will only reveal the grossest of ignition system problems, because it's testing the ignition system in a very non-demanding environment, at a very low power setting, typically 2000 RPM for Lycomings or 1700 RPM for Continentals. And if you follow the POH, which I don't recommend, at a rich mixture, I actually recommend doing the ground check at a pretty aggressively lean mixture. But the POHs all say mixture full rich and so on, which is not really good advice, but that's what they say, and that's what most people do. A low power rich mixture provides even a marginal ignition system can ignite a mixture like that. So the ignition system can be in pretty crummy shape and still pass that kind of a mag check.
Yep.
So the test that we like to do is one that's in flight, at moderately high power, 65% or something, some comfortable cruise power, and at the leanest mixture that the pilot is comfortable with, and preferably a lean peak mixture, because the higher the power and which means the higher the instantaneous combustion chamber pressure, and the leaner the mixture, the harder it is to ignite. And for the purpose of this test, we want the hardest possible mixture to ignite, because we want to test the ignition system under the most demanding conditions, to make the test more sensitive and to make the test reveal incipient problems with the ignition system that aren't bad enough yet to cause problems, but are early warnings of something that we really need to take care of before they get worse. So we recommend, setting the aircraft up in cruise at a lean mixture, and then doing a mag check, but a very slow mag check. We recommend turning off, say going to the left mag and leaving it there for a while. And how long a while is kind of depends on the sampling rate of the engine monitor, but we would like at least 10 data samples running on that one mag. So if the engine monitor is a modern one that samples it once per second, then 10 seconds, we'd say on the one mag. If the engine monitor is, say, an old JPI EDM 700, we recommend programming it to its maximum sampling rate, which for the EDM 700 is every 2 seconds, and we'd want to be there for 20 seconds, which is 10 sample time. The default sampling rate for an EDM 700 or most of the old JPI monitors is every 6 seconds, which means you'd have to stay on one mag for a whole minute. That's why we kind of recommend cranking up the sample rate. And then going back to both for 10 samples, and then going to the other mag for 10 samples, and then going back to both. And that completes the ignition stress test part of the flight test profile.
What's interesting, Mike, is some people are nervous about doing that.
Well, they shouldn't be nervous. First of all, if the engine passed the crude mag check that you do before takeoff, you're pretty sure that you don't have, that neither mag is dead. So nothing terrible is going to happen. But if in the worst situation, where say a mag completely went dead, you would turn it to one mag, and if you turn it to the good mag, you'll immediately know that something's not right, because the EGT bars won't rise, and you'll say, the EGT bars didn't rise. I must be running on this one mag.
All the time.
Yeah, exactly. And at that point, you have all the information you want to know, and you don't proceed. If you are unlucky and you go to the bad mag, the engine will quit. And at this point, you just have to remember one thing. If the engine did, and this is a very low probability event, obviously, but if the engine did quit, and then you just did the instinctive thing, which was to say oops and went back to both, you'll probably hear a pop. Now, the pop's probably not going to hurt anything. It's just going to startle you. And the reason you heard the pop was because if you turn off the ignition system, the engine's still turning. It's still bringing in fuel air mixture, and it's not igniting it, and so it's sending it out the exhaust. So then when you go back to both, the exhaust system is full of unburned fuel air mixture, and when the engine lights back off, it's going to ignite that stuff, and it's going to make a funny noise. I've never heard of it hurting anything, but it startles a lot of people. If you would like not to be startled, and you'd like to be really, really kind to your exhaust system, the right thing to do is, if you go to one mag and the engine quits, pull the mixture idle cut off, turn the mag back on, then bring the mixture up and start the engine that way, and then you won't get the pop.
Right.
But I mean, I've been doing this for more years than I care to talk about, and I've never ever had a problem doing it, because what we're talking about is would be the most extraordinary event of a mag that was fine on the ground and then went totally dead in the air. That
Right.
just doesn't happen very often.
Yeah, I think there's just people, I've certainly heard from some of them, that are always a little nervous about going and touching a control that they just don't normally touch in flight. And one of the pieces of advice I give them is watch your hand while you do it, because the one thing that could happen that might startle you is don't go to off. Keep yourself going to left and right. Look at what you're doing. You will get startled if you accidentally go and flip it all the way over to off.
And if you did go to off, the same caution applies. If you do go to off, the instinctive thing is to go back to both, but what you really ought to do is pull the mixture control, then go back to both, then push the mixture control back, just to avoid the possibility of what's called an afterfire, which is what the official name of the pop is.
So,
but anyway, by gathering this data, there's a whole lot of stuff we can tell by looking at the data. First of all, if we have a marginal spark plug, and then when we run on that one mag for 10 sample times, when we look at the trace, we'll see that the EGT for the cylinder with that marginal spark plug is very ragged. And the reason it's very ragged is because the marginal spark plug is igniting the mixture successfully sometimes and failing to ignite it sometimes. And so we're gonna see that very clearly in the EGT trace, and that's why we want 10 samples worth to be able to see that. Another thing that we'll often see when you do this in-flight mag check is that the EGTs will rise when you're on one mag, and they'll go back down, and then they'll rise on the other mag, but they won't rise the same amount. Now, it's perfectly normal for say odd cylinders to rise more than even cylinders on one mag and to reverse on the other mag. That's normal. But if in the aggregate the EGT rises significantly more on one mag than the other, that's indicative of the fact that two mags aren't timed the same. And on most engines, they're supposed to be timed the same. So when we see a split time magneto, which again is very clear from the data, we can't quite tell which of the two magnetos is the one that's wrong, but we know that one of them has to be wrong because they're not timed the same. So we then suggest rechecking the timing. And of course, we talked a little earlier about just how critical mag timing is, that you really need to be within a degree. And if it's advanced, more than a degree or so, you're going to see high cylinder head temperatures. So anytime we see a split mag condition in an ignition stress test, we suggest getting out the buzz box and checking the mag timing carefully and figuring out what's wrong. The other test that we do in the flight test profile is this mixture distribution test or gamma-lean test. And basically what that is it's a series of very slow, smooth mixture sweeps going from a rich mixture to a very lean mixture. Normally, we lean it very slowly until the engine starts running quite rough, and then we gradually richen it again to a pretty rich mixture, and then lean it again until it starts running rough. Do that several times and try to do it as slowly and smoothly as possible. And what we're looking for is to be able to identify where each individual cylinder reaches peak EGT and determine what fuel flow each individual cylinder reaches EGT at. If the engine monitor captures fuel flow, then that's ideal, because we can tell. In fact, we have a software tool that we just point at the data that pops out with all the answers. If the engine monitor does not monitor fuel flow, then somebody in the cockpit has to actually write down the fuel flow as each cylinder goes to peak. That's one of the reasons that we recommend, when people ask us about engine monitor installations, we always recommend that they include fuel flow as part of the engine monitor. Most modern engine monitors have that as a feature.
Do you worry at all by going slowly there? Obviously, you don't want to linger in any point of there that is kind of in the red box as
Right. We recommend doing this at 60% power or less, so that basically there isn't a red box.
Okay.
Because we are going very, very slowly there, and that's a very good point, Jeff. We wouldn't want to run this test at 75 or 80% power, because it would be abusive.
Right. So your other
we recommend doing it at a low power cruise.
Right. So your ignition test is generally at high power, and your fuel flow test is generally at lower power.
That's right. Just to make sure that we're not doing anything abusive. And what we're trying to do is determine, which is the richest cylinders, which are the leanest cylinders, and most importantly, how far apart they are. And we measure the measure of quality there is what's called a GAMI spread, and it was developed originally by George Brawley at General Aviation Modifications Inc., who are the guys that invented the GAMI ejectors. And it basically is you take the fuel flow at which the first cylinder to peak reaches peak, which would be the richest cylinder, the leanest cylinder. And then you take the fuel flow at which the last cylinder peaks, which is the richest cylinder, and you look at the difference. And the difference, which is measured in gallons per hour, typically is called a GAMI spread. For fuel injected engines, we want the GAMI spread to be something less than 1 gallon an hour normally. If it's more than 1 gallon an hour, the engine probably won't run smoothly with lean mixtures. And there'll be some other consequences having to do with uneven cylinder head temperatures and stuff. And so we will then look to see which cylinders are the leanest. The first thing we normally would recommend is cleaning those nozzles and seeing if it makes a difference, repeating the test. If cleaning the nozzles doesn't bring the GAMI spread to an acceptable level, then we start talking about changing the size of the nozzles to bring the cylinders closer together, putting larger nozzles on the leaner cylinders or smaller nozzles on the richer cylinders in order to bring them all in line.
So you only focus on cleaning the ones that are leanest?
Yeah, in fact, in general, we don't like to do prophylactic nozzle cleaning unless we see some indication on the engine monitor that there might be a dirty nozzle. Okay. If the GAMI spread is good, and we like to try to bring it down to about 0.5 gallon an hour or less, then there's no reason to mess with the nozzles. And what we found in practice, and I've talked to George about this, and he has the same experience, is that when mechanics clean nozzles, they're at least as likely to contaminate them as they are to do any good. We really don't like to see the fuel system taken apart. Now, if you think about fuel nozzles, they're self-cleaning. They've got a very effective solvent running through them all the time.
Exactly.
And the only times, for example, I've ever had restricted nozzles on my airplane in the 32 years that I've been flying and maintaining it, is right after maintenance where the fuel system was opened up. Because anytime you open up the fuel system, there's the opportunity to get some sort of foreign material in there, which will propagate its way through the fuel system until it gets to a really tiny orifice, which is usually the fuel nozzle in a fuel injected engine. If the fuel system is closed up, the fuel gets strained 3 times in a row. It gets strained in the yeah, 3 times. It's strained through a fairly coarse screen, and typically at the pickup in the tank. Then it goes through a finer screen in the gasculator or fuel strain or whatever you want to call it. Then it goes through an even finer screen in the fuel control unit or fuel servo, and it's going to be squeaky clean by the time it gets to the flow divider and into the nozzles.
Exactly.
So normally, opening up the fuel system causes more harm than good. So we try not to do it unless we have to. And then we want to do it with, in clean room conditions, preferably, with gloves on and stuff like that. So we don't, it's so easy to get a little glob of grease or something in there when you have the fuel system opened up. So we don't normally recommend doing prophylactic nozzle cleaning. A lot of shops like just normally routinely take the nozzles out and put them in a jewelry cleaner full of Hoppies number 9 every year. We don't recommend doing that unless there's some indication that there might be a restriction, and that would show up with a GAMI test that has a wide spread and showing some cylinder that's a lean outlier. Then we would, before we start messing with a different size nozzle, we'll say take the nozzle you got and clean it.
Right.
If it was working okay, 6 months ago and it's not working okay now, maybe it just got dirty. So.
Right. Well, it makes perfect sense, and I'd like to certainly, again, put another endorsement out there for anyone watching to go and take advantage of your services. I think the free services are amazing, but the subscription services that you offer, there's some really incredible value in that. And so, I mean, obviously we're out of time tonight, but there were so many questions that came in we didn't get to. Of course, so many topics, which is why I love it that you're such a regular guest here with us on SocialFlight Live. Really appreciate that. And of course, you are going to be back again September 1st with us.
Yes, I will. Yes, I will. I don't know what we're talking about yet, but I'm sure you're going to tell me.
I'm going to try to get you to talk about Lena Peak. We'll talk about it. We'll start hitting some of the more questions that people have submitted here, and we'll have another fun conversation. So I'd just like to thank you again for taking the time to join everyone here. We had a packed house, and it's really great. You, of course, always live up to your billing as the best known A&P and IA in General Aviation. There's a reason for that.
Yeah, it looks like we came pretty close to hitting that 1,000 limit tonight, didn't we?
We did. I've got a lot of apologies that are going to be sent out to the people because a lot of people hit up against that tonight.
Oh, really? Well,
yeah.
I don't know if that's good news or bad news. I think it's pretty good news. I
exactly.
Like to have a packed house. Jeff, I just want to mention one more thing before we quit, just because it's a timely thing. Savvy has a 24/7 breakdown assistance service. One of the things that we do to help people who are stuck in airplanes away from home with problems. And during the COVID-19 lockdown, we decided to make that service free. And we've had a lot of people take us up on it. That free period is officially going to end day after Labor Day. So I think it's September 8th. And those people who have signed up for the free service will at that time get I'm not going to say what it is, but it's kind of an unbelievable deal. If they want to continue the service on a paid basis, it's going to be a huge discount from what we normally charge. So anybody who might be interested in that, you've got till September 8th to sign up for the free service and to get in on the deal. And I just wanted to mention that because it's coming up.
I appreciate that.
Coming up soon.
You certainly have my support on that. I mean, that your free breakdown service and then paying for it at even at its normal price is a huge value. And so it's good to know that to everyone out there, message sign up for the free service now, get the deal, get the discount. You're going to want to take advantage of it after Labor Day when that offer comes through for you.
Yeah,
Well,
we've
Mike,
had some fabulous breakdown saves
oh,
over the last few months that make really interesting stories.
they really are, and I love those stories. You save people so much money both on a regular basis and on a breakdown basis, and that I think is one of the things that makes you so popular.
Well, thanks, Jeff. Appreciate it. I
Absolutely.
look forward to the next time we do this.
Oh, it's always a pleasure. So everyone, Mike Busch, CEO of Savvy Aviation. So we will be back again with Social Flight Live next Tuesday. Of course, AOPA President Mark Baker will be joining us on the program next Tuesday. So be sure to tune in for that. It's really going to be a very informative and inspirational evening, learning about his story and what's going on in AOPA during the crisis and some of the things they're doing moving forward. So lots of good information to come from that. Then we have a Social Flight adventure that's going to be going on, that's planned at least at the moment, unless COVID does something to block that, that we have. So we're currently planning on being off for 2 weeks, and then we are back August 25th with a T51 Mustang build night. We are going to talk all about this project behind me. And we're going to walk through it. We're going to show you exactly what's going on with that project. Should be a lot of fun. Take your questions. And then, of course, as we just mentioned, September 1st, Mike is back with us. So again, thank you all so much for joining us. Apologies we didn't get to your questions. We'll be sure to follow up with that with more programs down the road. And thank you again. Blue skies.